commonly observed reactions in organic chemistry are like as you can see, there is first of all it is addition, which is further subdivided into electrophilic, nucleophilic, free radical. Then there is substitution, where again it is classified as electrophilic, then nucleophilic, then free radical substitution. Then there is elimination reaction, which is classified as E1, E2 and E1CB. And then there is rearrangement reaction. Here we have just considered the primary rearrangement reaction of carbocation only. There are many other rearrangement reactions, so we are concerned mainly with the carbocation rearrangement. So just to begin with, first of all we'll start with the electrophilic addition reactions. So first let's see what electrophilic addition reaction is. So when we say electrophilic addition, a very simple meaning is like this. When we say it is electrophilic, that means it is the addition of electrophile, nothing else. So it is addition of electrophile in the very first step. Electrophile in the first step. So this is the key for this electrophilic addition reaction. And so if you take this as an example, so this is the characteristic reaction of alkenes. Alkenes, majority of reactions of alkenes are related to electrophilic addition reaction. So as an example we can say, we can see here, like taking a simple alkene like C-double-bond-C, where these two bonds are there, another two bonds, taking H plus is the commonly used electrophile, and so here is, this is generating a carbocation like this, plus, and H is added here, and in the next step nucleophiles are getting attached. So overall it is addition of a reagent over carbon double bond, and since in the very first step this H plus is attached to the double bonded system, so we call this electrophilic addition reaction, as the reaction is initiated by the electrophile. Now this is the simplest case where there is nothing different. It is symmetrical alkene has been used, and so simple H plus is used, so we are getting this kind of product. But what else if it is something else, like if the reagent itself is different? Like for example, if I just take unsymmetrical alkene, if I just take this one C-double-bond-C and one CH3 is attached here, here it is H, here it is H, and then adding HCl to this. So what we need to identify is governed by the law called Markownikoff's rule. So this Markownikoff's rule also sometimes pronunciated as Markownikoff's rule. So this is a very important rule. In general it is expressed as more gets more. That is a simple relation that we observe in that real life as well, like dissolves like, or something like that kind of relation. So here the simple rule, this is stating if the alkene is there, like here it is, so where is the more number of hydrogen atom? So we can easily see that on the left hand side terminal we can have more hydrogens. Here it is 1, here it is 2, directly attached to the carbon. Here only 1 is there, so we can say more gets more, more hydrogen is there, so more another hydrogen would be attached to this particular carbon. That is one way of predicting the product. But when it comes to conceptual correctness, what we should understand and what we must realize, that it is the carbocation stability which determines the orientation of the groups, or which determines the position of the groups. So according to this rule, that in case of unsymmetrical alkene, in case of unsymmetrical alkenes, negative part of the reagent gets attached to most stable carbocation. Or other way around, we can also say like this: positive part attach in such a way that it generates most stable carbocation. So this is what the key is, and this is very important to understand and remember as well. Unless you remember this, you won't be able to identify what exactly the product would be. So there are two statements, two different way of saying the same statement. One is saying like this: carbon positive should be more stable, that is positive part of the reagent must be attaching to that carbon which generates most stable carbocation. Or the other way around, we can say negative part of the reagent goes to most stable carbocation. And so in this way we can identify the product in the previous reaction, where it is the reagent is HH CH3 and H is here, so H plus. So looking at this, we should analyze where is the more stable carbocation generated. So since generation of carbocation itself is the determining step for this reaction, therefore this carbon where more number of methyl group is attached, or more number of alpha carbon having more number of alpha hydrogen is present, so we can say that is the carbon where this H plus is going to, negative part would be going to attach to that particular carbon. So all carbocation is generated at that particular carbon. So basis this, we can say in the very first step it is generating HH and one more H is getting attached here. So here it is, and it is generating H, another is CH3, and here is positive charge. So then the nucleophile, or which is Cl minus in this particular case, is getting attached to generate CH3, CH3, Cl. So let us take another example. If we have this one, where HBr is to be added. Now in this case, the two bonded center where possibility of formation of carbocation is, first is this, another is this one, this is 2. Out of these two, where is the most stable carbocation is expected? So definitely we can see and identify this particular carbon, first one, H, generated more stable carbocation. Therefore negative part of this is what? Negative part of this is Br minus. So Br minus is getting attached to this particular carbon, that is carbon 1, and H plus is going to attach to this particular second carbon. And so the major product of the reaction is Br here and H here. Though we don't need to write H, but just to show this to make it more clear. Let's take one more example, like this one. Just take this. If I would have taken CH3 double bond HCH3. So in this particular case, if I take HOCl, now two different things are there. First is, how is this HOCl being broken? So if I just take this HOCl would be broken in this way. HOCl, so it is forming OH minus plus Cl plus, so it is HO minus plus Cl plus. Therefore this is one part of the reaction that we need to identify a reagent, how it is getting dissociated. Second part is, where is the negative and positive parts? So if I just look at it, so we find that since this carbon has more, so this OH minus is going to be present here, whereas Cl positive would be taken up by this particular carbon, and so the product would be CH3 CH3, here it is OH CH3, and here it is Cl. So this is the major product of the reaction. Take up one more example, which is very important, like this one. If it is a double bond and it's there NOCl. So first of all, what we have to identify, what we need to concentrate is to know how is this NOCl is going to break. So when we write the structure of NOCl, is it something like this, NO and Cl? It's not. This is wrong description. So remember, what is the basic structure of NOCl? It is something like this: N double bond O, and here is Cl. So out of these, we can say N will acquire partial positive charge and Cl will have negative charge. Therefore the product would be something like this. So Cl minus is getting attached at this particular carbon, and Cl is here, and NO is getting attached at this particular carbon, and double bond O. So this is the product of this electrophilic addition reaction. Now how is the addition of water takes place? So if I would have taken a similar example with water, so is there any reaction? No reaction at all. No reaction. Why it doesn't react? This is an important question. So here the important thing is H2O. H itself is not an ionic compound. It is not dissociating like H plus plus OH minus. So this is not the case. A very small amount of H plus is present with this OH minus, so that is not sufficient to activate this alkene to make bond with H plus. So what we need is we just add a small amount of catalytic amount of H plus, then add H2O, so magic happens. And thus in that case, the moment you are adding this, so H is here and a carbocation generated, and then there is H2O, so it is forming H. And now since nucleophile is this oxygen, so donating electron to this one, and thus we have O, H, H positive minus H plus from this to form this compound. So this is some classical example of electrophilic addition reaction.